Okay. Now I would like to go ahead to continue to talk about the matrix. What are matrix? We talked about operator already. The operator is to rotate, right, the vector in the hyperspace. We talked about that already. And they're represented as the matrix, right? Like the CNOT gate, Hadamard gate. Good. But there's a special matrix called the Hermitian matrix. First, let me introduce that there's something called adjoint matrix. So what is this? So if A is a matrix, then A dagger, which is equal to A transpose followed by complex conjugate, is the adjoint matrix of A. Okay, so for any matrix, you take the transpose and then you take the complex conjugate. Then that is the adjoint matrix of A. For example, if I have a matrix that is I, 1, 0, I, okay, its adjoint matrix, it is the dagger. So it is equals to I, 1, 0, I transpose dagger, complex conjugate. What is transpose? You will just draw a diagonal line and then flip over the element. So all those on the diagonal are still there. But then I'm going to swap this ij. This is element first row, second column. It becomes second row, first column. Second row, first column becomes first row. Second row, first column becomes first row, second column. So I'm doing this reflection, right? Do you see this? It's the same for other higher dimension. But besides this transpose, we will going to take the complex conjugate also. Okay, so we say this is the adjoint matrix of the original matrix. Okay, this matrix is the adjoint matrix of this matrix. Just some definition. Okay, nothing special at this moment. But then now we're going to introduce, for some matrix, its adjoint matrix equals to itself. Then we call A is the self-adjoint or the Hermitian matrix. This is a very important matrix in quantum mechanics. Okay, so what we have just said, basically just say self-adjoint. What we basically just say that we just gave a definition of adjoint, and then if it equals to itself, then it is a Hermitian or self-adjoint matrix, so we have A dagger equal to A. Okay, for example, I have something called sigma y we're going to study later, which is 0, negative I, 0. What is the adjoint of sigma y? Well, first I will do a transpose and then followed by the complex conjugate. When I do transpose, I just swap the about the diagonal, right? So I have moved this one to here and this one to here. So I just swap them. And then apply the complex conjugate, then it will get negative again. This one become I, which is just equal to sigma y. Yeah? So this is a Hermitian matrix. Okay? Then what's so special about the Hermitian matrix? The Hermitian matrix has the eigenvalue real. Okay, I'm not going to prove it, right? You can read my book, right? Otherwise, just take it for granted. Their eigenvalues are real, right? So what is eigenvalue? Eigenvalue of a matrix is that you can find a vector V. So the matrix times the vector equals to a value times the vector. Just a pure number. This is a number. Okay, right? And this is a vector, right? And this is a matrix, right? For example, you will be able to find sigma y, right, times a certain vector. I kind of forgot. I think it can be let me don't use sigma. I forgot the eigenvector of sigma y. Let's say sigma z, right? I'm not going to talk about sigma z yet, but I did not give you. Or z, I actually gave you z, right? I can tell you z times a certain vector equals to -1 times that vector, right? And z is what we talked about earlier, the z gate. It times 0, 1 equals to negative 0, 1. You can see that, right? And this is like -1 times 0, 1. So the eigenvector here is 0, 1, and the eigenvalue here is -1. Is that okay? Yeah. Okay. It's just saying that I have this matrix times a vector. It's just equal to a number times that vector. So basically in the space, you can see that it does not rotate the vector. When you apply a matrix to a vector, you expect it to rotate. But for an eigenvector, when you apply the matrix to its eigenvector, it only scales the vector instead of rotating the vector. Okay. But here I want to say that this, if the Hermitian, it is a Hermitian matrix, that matrix must have a real eigenvector. And why this is so important? Why? That is because of this Bond's rule, right? So it is said that if an observable, when we do measurement, those are observable, we get something, right? They always correspond to a Hermitian matrix, right? So we will gradually understand what it means. But for example, when you measure the spin, it corresponds to the Pauli matrix, right? For example, the spin it might be correspond to a Pauli matrix sigma z, right? Which we just discussed, right? When we measure it with some normalized function, right, in the state, the result will be one of the eigenvector. They basically say that when I measure the spin and the corresponding matrix must be Hermitian, because the eigenvalue we measure must be plus minus 1, right? You measure the spin is either going up or going down. Okay? And then the probability of measuring the a certain value, of measuring a certain value is equal to the projection operator corresponding to that lambda. Now, so this is a little bit troublesome, right? You don't know what I'm talking about, right? I'm going to explain it. But the point is that I want you to now, right? We are rather fast because we discussed in other class, but you can take it for granted. The point is you agree that every operator, every matrix, they rotate the vector, right? That's what quantum computing about. You rotate the vector in the hyperspace. There is a special vector, a special operator They are Hermitian, means this one, right? They are Hermitian because they have real eigenvalue. And why? Because all the Hermitian operator, right, will correspond to some observable, or maybe I should say all of the observable will correspond to some Hermitian operator. For example, you measure the velocity, measure the position, or measure the spin up and down. You have a corresponding Hermitian operator. What you measure are actually the eigenvalues of this Hermitian operator. Right? So, for example, here I told you that Z has an eigenvalue of -1 or +1. I did not show here because it has two eigenvalues, right? So when you measure the spin, you can be either plus or -1. And this plus -1 turned out to be the eigenvalue of Z. And because it's the eigenvalue of Z, and because it is measurable, it's observable, it's our real life, it must be a real number. It cannot be a complex number. Okay, so these are the relations between Hermitian matrix, observable, eigenvalue, and the real value of the eigenvalue, right? So I hope you can associate this, right? Now, but what is the probability of measuring the eigenvalue? We actually know already, right? We actually know that already. Remember that if I say I have a state which is psi equals to alpha 0 plus beta 1, we say the probability of measuring 0 equals to alpha star, or the magnitude of the alpha square, right? The probability of measuring 1 equals to beta star, which is the beta square. But this is not convenient. This is a simple case. We can see the coefficient, but we're doing derivation or whatever. You cannot do that, right? So the one way to do this is to use the so-called projection operator, right? So let's be patient. Let me tell you what is projection operator, okay? Oh, so this is spelling. I'm sorry. Right. So this actually is a projection, not project or project. This is a projection operator. So what does it mean? The projection operator of V, what does it mean? It means I want to project the state into V. Basically, it's doing inner product. I want to project it. But I need I have an operator help me to do that. The projection operator equals to V. Now, this is a little bit confusing. We have learned about inner product, right? Inner product of V is what? V. This is the inner product. It gives us a number, a scalar number. But what is this? This we call it the outer product. And can you get what it gives us? It gives us a matrix. The easiest way to see this is just to look at an example. Okay, for example, what if V equals to 0? How do we write that as in the column form? Well, I have one part of the 0 state, right? So it is 1, 0. What is the bra version of V? Well, you take the row version and take complex conjugate here. I don't need to do that because they're all real number, right? So what is V? Well, it is equal to 1, 0 times 1, 0 in this way. Again, through the matrix multiplication, first row times first column of this guy. This gives us 1. First row times second column, it gives us the element of the first row and second column, which is 0. And then second row times the first column, it gives us the second row and first element, which is 0, and then also 0. So this is a matrix. Okay? So this is the projection operator. We will call it P of 0, right? So here I forgot to write it. This I will call it the projection operator of V. Okay? It means the projection operator corresponding to V. Okay, so this is definition, right? Not difficult, right? Just memorize, okay, I have projection operator, which is the outer product. Fine, nothing special. But what's special is here. Let's take a look at an example. What does it do? Okay, for example, I have a state equals to alpha 0 plus beta 0, beta 1. Right? Again, a superposition, right, of the two basis states. What is the, when we apply the projection operator of 0 to xi, what do I get? Now let's do some exercise. First, projection operator of 0 is this. I apply it to xi. Yeah? So I can write it as 0, 0, alpha 0 plus beta 1. Yeah? Because psi is the whole thing, right? And then it's linear. Again, this is very important, right? Becomes 0, alpha 0, inner product with 0 plus beta 0 inner product with 1, right? Because I can bring this in and then bring this in, right? I can keep this out, right? If you want, you can bring this in also. It's the same, right? But they fulfill this associative law, okay? What is 0.0? What is 0.1? This is an orthonormal basis, as we said earlier, right? So this is just like x hat dot x hat. This is just like x hat dot y hat. Then, of course, this is 1 and this 0 because it's orthonormal. So the projection operator gives me 0 times alpha because the second term is gone, which is alpha times 0. You see that the projection operator take out the component of the vector that we are interested in from the total vector, right? So already this total vector is an addition, right? Like a vector addition of two components. By applying the projection operator, we get alpha 0. Okay? Now, so we don't want to go to too much math, right? I just want you to trust me. This is the case by showing you this one. So from now, I hope you remember, you construct the projection operator just by doing the outer product, and it's just like an operator applied to a vector. You will extract that components from there, right? So what is the probability of getting 0? Now let's think about this. What if I apply this, like what we said here, right? Instead of just projection operator on the state, we apply a bra on it. Sandwich it, right? On the left, apply the bra version or sandwich the projection operator. Now, on the left, this is a bra. So how do we do it? We need to take the complex conjugate, right? We also need to turn this to a bra version. Complex conjugate, turn to the bra version. This is like this one, right? Psi. Yeah? And then on the other side, we know that this is alpha 0 already. Yeah, we just done the calculation. Projection on P0 applied to psi equal to alpha 0. Now you again do the distribution law. You get the inner product of 1, 0, which is 0. 0, 0, which is 1. what you get is just equal to alpha star alpha, which is still alpha squared. So now you see that what we said earlier is correct, right? We can prove it with a more general form, but by just using this special example, you do see that the probability, right? This is equal to the probability of getting 0 during your measurement. So in summary, projection operator is constructed by outer product. You apply the projection operator to the state, you get the component of the corresponding vector you are trying to project to. Okay, like projection, like the shadow. Okay, and if you try to do the what we call expectation value of this projection operator, you will get the probability of that state. Now, then this can be generalized to many things, right? It will be useful in the future, right? But this is a good way to appreciate the outer product, the Hermitian matrix measurement, and projection operator. Okay, so please try to understand, right? And finally, for the so-called linear algebra, the last thing I want to say is we talk about the dual correspondence, right? We have the so-called cat. Let me see. Cat. And then we have the bra. Cat and bra are just like myself in this real world and the image, myself in the image. They somehow have some difference. Okay, the left and right got swapped. Okay, and if I apply matrix to the cat, it is just like applying the adjoint matrix from the right to the bra. So I just want to mention this. Okay, this one we discussed before already, right? How you apply the matrix to a vector and how you do the distribution law. The main thing is actually for this whole slide, I think I did not prepare well for this one. Okay, I know what was wrong with my, yeah. So what I want to say, yes, so we have dual correspondence from cat to bra, okay? And I actually forgot to say a few things also. If this cat, let me change this to, let's say alpha, right? If I have this cat is scaled by alpha, then its image will be scaled by alpha star. Just remember the complex conjugate. Okay, that's how it is scaled. Of course, this can be written as alpha star A. Okay, that is also okay. Right, that is the first thing. And then another thing that we want to say, this is the 1, right? This is 2. Yeah, I actually did not copy well, but I forgot to delete this part. But that is what I want to say actually, the dual correspondence. The vector on the left is the image, and then the bra, on the left is myself, and then the bra is like my image. If I scale myself by alpha, it's just like I scale my image by alpha star, which is the complex conjugate. If you apply operation to the vector, it's just like applying the the self-adjoint matrix of X, right? If X equal to X dagger, then yes, it's Hermitian. But now we don't know, right? It can be just adjoint. So we just apply the adjoint from the right to it. Okay? And we also have learned a few important rules, which is the inner product of two vector is equal. If you swap them, you need to apply the complex conjugate. Okay, and also, right, we are not proving, you can prove it easily. If we applied operator in this way, we sandwich the operator with the bra and cat. If we swap them, this is very easy. The whole thing, you will get a complex conjugate because this is just a number. Okay, and then this one, you will do the adjoint matrix for the operator. Okay, so this rule maybe we can try to prove in the homework, but yeah, we don't have enough time, but just you can take it for granted, but you do need to memorize this or have in your cheat sheet, right? Or you know that where to find them, go to Google or Wikipedia. These are important. Okay. One more thing need to say is about the unitary matrix. What is a unitary matrix? Yeah, what is a unitary matrix? We talk about Hermitian matrix, right? Recall Hermitian matrix. What is that? A equals to A dagger. Then this is a Hermitian matrix. What is a unitary matrix? U, just a name, you can call it A, right? Times U dagger equal to 1. Or you can say U dagger equal to U inverse. Okay, the difference is that one equal to itself, another is equal to its inverse. Or when you multiply them together, U times U dagger equal 1. This is a unitary matrix. And that's it. But why is so special? Because it preserves the inner product. In the U transformation. What does it mean? Again, what is a matrix? What is an operator? It basically just rotates your vector or transform your basis. Whatever. It is doing a rotation in the hyperspace to your vector or to your coordinate system. Let's think about this. I have two vectors, G and F. Right? Their inner product is what? Well, you can say it is GF. Fine. Right? You just, okay, this is the inner product. Now, what if I rotate the system or transform the system? Whether you rotate, let's say I rotate the matrix together, right, by U. Then this becomes U of G and U of F, right? I rotate them, right? So this can be NOT gate or Hadamard gate. I apply to it, then I rotate it. What is the inner product of them? What are they? Well, remember that just told you earlier. If you apply a matrix to the vector, its bra version is the bra version of the vector times the Hermitian, times the adjoint matrix. So the inner product is going to be G times the adjoint of U. The whole thing then do an inner product with U times F, right? Because this F now becomes UF. This G now becomes GU dagger, right? G still becomes UG. But however, when we're doing the inner product, we need to take the bra version, and the bra version is G times U dagger, right? What is this? G U dagger U F. What is U dagger U? If this is unitary, this is just equals to I, which means we can ignore it because I does nothing to anything. So it means that after any unitary rotation, the inner products are still the same. Now this is very important because preserving the inner product has some significant physical meaning. The relationship of the two vectors should not change just because you change your rotates the coordinate, right? So that is the importance of the unitary matrix, right? And because of time again, you can just memorize this. Definition you need to know, right? U dagger U to U minus, right? You can prove it if you have time. And the important thing is that they preserve the inner product. It's good you understand how this is proved because this really tests you the understanding of the dual space. How do you construct the inner product? How do you construct the bra version of a rotator vector and the associative rule? And then you prove that the inner products are not changed. Okay? Now we are talking about the transformation matrix. We're talking about the unitary matrix. So here I want to take this opportunity to finish this transformation matrix, which will be useful in the future. We won't go into detail, right? But we are talking about the transformation matrix. So what does it mean? So you might represent, we remember we have wrote down the vector psi, right? It can be equal to alpha 0 plus beta 1. And this is in the 0 and 1 basis. Yeah. I also showed you earlier, I can write it as, what is that? 1 over square root 2 alpha plus beta plus alpha minus beta minus, right? Let me check. I actually don't have cheat sheet for this one. Let me check, right? So like this, right? 1 over square root 2 plus a plus alpha plus beta and then alpha minus beta, right? This is in the plus minus basis, right? So again, as I said, this is just like 1 8 basis. This is like 1 dozen 8 basis, but it's 2D, so it's more transformation. It is troublesome if we want to if we try to derive in the way we did, right? We can actually construct a transformation matrix in this way. I can construct a transformation matrix. I call it U. It is called U. It definitely is unitary, but nothing to do with the last line. I just call it U. So how do I construct it? I'm going to construct it using this way. This is a matrix. So for the ijth element, okay, it is equal to the new basis I vector inner product with the O basis j vector for the ith row jth column element. Okay? And then with this, any new vector, right, is equal to U times the O vector. Okay, so maybe I should, let me write it in this way. Any, with this, then when we do the rotation, do the transformation, it becomes U multiplied by the vector. And any matrix, it will becomes, when we do the transformation, it becomes U M U dagger. Okay, so you trust me for now, right? That's how you do it. Let me see, actually. Yeah, maybe let me give an example. Maybe that will be the best instead of rushing to the poly matrix, right? Let's do poly matrix next time. I know, yeah, it would be better to do this. Let me give you an example. Let's just use the plus minus basis example, okay? So let me just add one more slide. I think it will be good to add one more slide on this. Now, let's just click. Am I recording? Yes. Okay. Let's take one example. I'm still using this example, plus and minus basis, right? Let's think about this. So I'm going to construct this poly matrix U. I mean not poly, sorry, the transformation matrix, right? Now because it is two-dimensional, so I only have the new 0, the first vector, right, times the O first vector, because there's zeros, the 0, 0 row and column, new 0 times the O 1, right? And then new 1 O 0, and then new 1 O 1. Okay, so what does it mean? What is the new 0, new 1 O 1 O 0, right? The O 0 was the 0 basis, right? Because we were the O coordinate system. The O1 is 1, right? The new one, we are going to transform to the plus basis, right? The O1 is actually the minus basis, right? We're transforming from 0, 1 to plus minus. So this is O1, O, and this is new. It's just like a Cartesian. You transform from x hat to x hat dash, right? This maybe you can think about, oh, this x hat. This is like y hat. And I transform it to x hat dash. This transform to y hat dash, right? So this is basically talking about plus inner product with 0, and then plus inner product with 1, and then minus inner product with 0, and then minus inner product with 1. Okay? If you remember the definition of plus, right? Plus equal to 1 over square root 2, 0 plus 1, and minus equal to 1 over square root 2, 0 minus 1. So the inner product, you see that is to find the common parts, right? Because once you break it to the bra and then dot product with 0, 0 and 1 is 0 because it's orthogonal. So this is plus 1 over square root 2, 1 over square root 2, 1 over square root 2, right? You just try it, you will see that this is negative 1 over square root 2, because in this case, you have this negative 1 inner product with 1, right? Negative, right? So you get negative 1 over 2. Hey, by the way, what is this? This is just the Hadamard gate. And indeed, that is what we know, right? Now, then, let me show you. If I try to transform the psi, right, is u times psi, which is equal to 1 over square root 2, 1, 1, 1, negative 1 times alpha beta, right? What is this? This is equals to 1 over square root 2, alpha plus beta, alpha minus beta. Do you see that? Alpha plus beta, alpha minus beta, right? After transformation, this one, I transform it successfully, and now I represent the thing in the plus and minus basis. Okay, so you can do the similar thing on the matrix also. Okay, so practice this, right? So this is the transformation matrix, and it's unitary.